Good morning. My name is Luca Possidente, and today I'll give a presentation about the numerical analysis of the torsional and flexural-torsional buckling behavior of compressed steel members at elevated temperature. I worked on this topic during my PhD at both the University of Trento and the Royal Institute of Technology in Stockholm. First, I will give you the introduction and the motivation to this work. I will then explain the main features of the parametric analysis I performed and give a brief recall on the existing norm provisions. The presentation and discussion of new buckling curve of proposals will follow, as well as the main conclusions and some indications for further research. So steel angles and built-up sections are widely employed in bracing systems or truss structures and are designed to withstand axial loads. So since they are subjected to compressive loads, torsional and flexural-torsional buckling might affect these sections. Truss and bracing systems can be found in structures which may store large quantities of combustible material, and hence the investigation of steel angles and built-up sections in fire is paramount. However, torsional and flexural-torsional buckling is not explicitly treated in the European norm for steel structures in fire, so Eurocode 3 Part 1.2. In order to understand if safe and accurate predictions can still be obtained into Eurocode, a numerical investigation of the behavior of concentrically compressed steel angles T and cruciform sections at elevated temperature was performed in this work. A parametric analysis consisting of more than 23,000 geometrically and materially nonlinear analysis with imperfections was performed. Concentrically compressed members at elevated temperature consisting of L, T, and X sections were investigated. 5 different temperatures, 400, 500, 600, 700, and 800, uniform and constant in the members, and 3 different steel grade as well were studied. The length of the member L was varied so that stocky to slender members were studied, but in order to limit the analysis to members of practical interest, only members with a length to width ratio bigger than 3 were studied. Initial geometrical imperfections were introduced in the models based on linear eigenvalue analysis. So in detail, each one of the analyses consisted of a 3 steps procedure. First, a linear eigenvalue analysis was performed in order to obtain the lowest buckling mode. This mode was then scaled to L over 1000. This means that the shape of the buckling mode was scaled so that the maximum nodal displacement was set equal to L over 1000. The scaled mode was then used as initial geometrical imperfection and introduced in the model. Finally, the analysis of the imperfect column at elevated temperature was performed and the resistance of the column was obtained. So in this slide, we have the tables of the investigated sections. Single equal leg angles were studied, as well as T and X sections obtained by couple 2 or 4 angles. Class 1, Class 2, and Class 3 sections were studied according to the classification at elevated temperature. The numerical model employed in the analysis was different for monosymmetric and bisymmetric sections. In the first case, 3D beam finite elements were employed in the analysis, and simply supporter members were investigated. Instead, in the second case, shell finite elements were employed since imperfections associated to a pure torsional buckling cannot be defined in beam elements-based analysis. Moreover, clamp members were investigated as the definition of simply supported condition is not straightforward in shell models. So in this slide you may see the numerical results only for T sections consisting of 2 coupled equal leg angles. We have the results for all the temperatures and for the 3 different steel grades. So here and in the following slides, the failure loads divided by the yielding load are plotted in order to obtain normalized values. According to the Eurocode for steel structures in fire resistance of compressed steel members should be reduced by the key factor. So the key factor depends on the generalized imperfection factor eta and on the non-dimensional slenderness at elevated temperature lambda theta. This non-dimensional slenderness at elevated temperature in turn depends on the non-dimensional slenderness at ambient temperature, which is defined in the Eurocode 3 part 1.1. And in this slide, you can appreciate what we obtain if we superimpose the Eurocode backlink curves prediction to the numerical results showed previously in the previous slide for T sections. In general, numerical outcomes and predictions from the Eurocode are, as you may see, not in good agreement. So to better represent the behavior of the members subject to torsional and flexural-torsional buckling, a new buckling curve was proposed based on the Eurocode curve. The difference between the two curves consists in the definition of the generalized imperfection factor eta and the 3 parameters beta, gamma, and lambda 0 numerically define the new buckling curve. For each cross-section type, you may find the values of beta, gamma, and lambda 0, giving the best predictions in the table shown in this slide. So here we have the predictions from the buckling curves plotted against numerical results. The figures shows the results again for T sections, obtain coupling to equal leg angles, but similar observation can be taken for all the cross-section types we investigated. The Eurocode 3 part 1.2, as you may see, provides both over and unconservative predictions depending on the slenderness, whereas the proposal in green much better reproduces the numerical outcomes. In order to better compare the predictions from the two backlink curves, for each member, results are presented in this slide, coupling the numerical results to the associated backlink curve predictions. So, since safe predictions are obtained when the ratio between predictions and numerical results is less or equal than 1, the bisector line in these pictures defines the safe-unsafe limit. And as you may see, the figures show that safer predictions are obtained for the proposed curve in green. In detail, the predictions of the proposal are much better distributed in the -10 to 0 range. A statistical investigation based on the results of the previous slide was performed as well. A normal distribution was assumed, and as you may see here, the statistical investigation shows that the probability of safe prediction is always higher than 96% for the proposal, while it is always less than 51% for the Eurocode. This work can be extended to the American norm as well. So according to the American norm, the nominal strength for compression in fire situation should be obtained with the first equation shown in the slide. As for the Eurocode, an equivalent reduction factor K can be derived with some math to be compared with numerical results. The parameter N can be identified and modified to obtain an improved formulation for members subjected to torsional and flexural-torsional buckling. And as you may see in the table in this slide, we have the parameters A, D, and lambda 0 again that numerically define the best solution. Predictions from the buckling curves obtained with the original and the new formulation are shown again for T sections, obtain coupling equal leg angles. In the paper, faux I would say that though more accurate prediction than the Eurocode are obtained, the American norm still provides both over and unconservative predictions, and this again is depending on the slenderness. So the proposed modified curve instead, as you may see, much better reproduces the numerical results. Again, in these figures, we show that safer predictions that are much better distributed in the -10 to 0 range are obtained with the modified curve. The statistical investigation shows that probability of safe prediction is always higher than 95% for the proposal. The American norm predictions are much safer than the Eurocode. However, improved prediction can still be obtained with this modification. And in particular, in the case of X sections, a value of safe predictions that was slightly lower than the original one was accepted for the proposal based on the American norm. And this is since a much better distribution, higher frequency, and a mean closer to 1 was obtained with the proposal. So in conclusion, the Eurocode 3 Part 1-2 provisions can lead to both over and unconservative predictions depending on the slenderness at elevated temperature lambda theta. The proposed backlink curve for the Eurocode allows for improved predictions. Statistical investigation proves also that the proposal is reliable and safe. And the proposed backlink curve ensures probabilities of non-exceedance of the safe and safe limit higher than 96% for all the investigated section types, so L, T, and X sections. A modified curve based on the formulation proposed in the American norm can be defined as well. And though more accurate than the Eurocode, the American norm still provides both over and unconservative predictions, while a better distribution can be obtained with a modified formulation. And the proposed backlink curve ensures, in this case, probabilities of non-exceedance of the safe and safe limit higher than 95% for all the investigated section types. In future developments, experimental investigations would be beneficial. Moreover, coupled sections were studied as single integral members, according to Eurocode 3 Part 1-1 provisions, assuming that the spacing of the connections is short enough. However, more refined finite element models could be employed in order to account for the influence of connecting plates or buttons. Thank you for your attention.